Hello and welcome back to Mars. I'm Mick, we're playing Stationeers. Now today we're back at our programming workstation here, and today we're going to have a look at numeric encoding or data encoding. So what is it? Why the hell would I want it? Well, as you're programming stuff, you may eventually outgrow your humble IC there. With only 6 connections and 128 lines of code, you could eventually write a program that's either too big to fit in one chip, or you don't have enough pins to actually operate all the devices you want, so you've got to split your program over 2 separate chips. And having your program in 2 separate chips means you've actually got to communicate between the 2 of them. Right, so the trick is if you have run out of pins, which is probably the most common one I most run into, to transfer any process variables you have from one chip to the other, you will need to use some of those pins, which you don't have many of, to actually communicate data out towards another chip, say one like this one here. Now, you can do it by passing values out via logic memories. Now, if you want to pass out a number of them, you can hook up a number of logic memories, but once again, each one of them will use a pin, which you don't have enough of. So if we use data encoding so as we can actually combine a heap of process values into a single number, so then we can just pass a single number which then contains all the different values you needed to pass, and then the chip on the other side can then receive that single value and decode everything from it. Now I'm using as logic memory here. You can write directly from one chip to the IC housing of the other chip, which means you don't need to use a logic memory, which is handy because using logic memory will get you a one-way communication. If this one then has to talk back to that one, you'll need to use another logic memory, which means you're using up 2 pins on each chip. Whereas if I get this one to use 1 pin to write directly to the IC housing of that chip, and then get this one to use 1 pin to write directly to the IC housing of that chip, they can communicate 2 ways, and they've only used 1 pin each chip. That's all nice and well, but how do we go about this? Right, so what we're going to do is a very basic one, is we have 4 switches, and we're going to combine the on-off states of all those switches into a single value, which I'm going to use here. Now, all the switches have is a basic on or off situation. So it's very much like just a 1 or a 0 for each of them, so it's going to be basically a binary number. So we're going to use binary encoding to move all these switches into a single binary number or a binary value, which will represent decimal because I can't display binary numbers. Then pass that to the other chip, which we can then decode that and maybe switch on some lights or something like that. Late. Yeah, later. Wait for it. Right. So let's get coding. So I've got the levers hooked up. Lever 1, 2, 3, and 4. Yeah, I've put a lot of thought into those names, and they're connected up here. We've got the display, our 4 switches, and the memory. Okay, and in it here we have them aliased. Alias is well, whatever. We've got them defined here as we named them all. Once again, lever 1, 2, 3, 4, our memory and our display. Now, confirm that one. Now, so how we're going to do this one is this one will have a position of an on or off, which we can represent with a 1 or a 0. Now, we don't want any of the other switches to duplicate that one there. So if we call that one 1, well, this one we can multiply by 2. So that one will either be a 1 or a 0. That one will be a value 2 or a 0. If we switch them both on, that'll be a 3. So we can't call this one 3. We'll call that one 4. And once again, if I switch off any combination of them, or all of them will be 7, which means that one will have to be an 8. This is, of course, your binary values. Go away. So 1, 2, 4 and 8, they're just multiplying by 2 each time. So 1 is, we're using a base 2 number, which is your binary. So 1 will be 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. And you can keep going, but that's how many pins we've got, so we'll just call it quits there. But you can go over 16, 32, 128, etc., etc. So all we're going to do is read each of those switches and multiply by the corresponding indexer, and then just add them all together and we shall have our coded number. Simple. Right, so we shall start and put in a yes. Oh, great spelling. We're off to a good start. We shall yield. So I might actually just alias a data. We'll put that in as R10 as a register. So we shall load into data from lever 1 setting. Now the index of that is 1, which you can multiply by 1 if you really want, but that's pretty pointless, so we'll just skip that one. Right, so that's our start there. So we shall load into R0 lever 2 setting. Now lever 2 is a 2 for our index, so we shall have to multiply R0 equals R0 times 2. And we shall add data equals data plus the new value R0. And that's it. So we can just repeat that for each of the other switches. So shall copy. And that will be for lever 2, lever 3, and lever 4. And we multiply them by 2, by 4, and by 8. That's not an 8. That's an 8. I know numbers. Right. So we'll just load them, multiply them by their index, and add them to the total. So we shall save to the display setting, not R0, data. And we shall also save it to the memory setting data. And then jump back to the start. That looks right. Confirm, export you, no errors, we're all happy. So if I flick that, we should get a 1, which we do. Flick you, should get a 2, should be a 4, and should be an 8. Right, so each of the levers are indexing now, so if we put in multiple ones there, it adds them together. Now because this is a binary number, with this switching there, sort of every unique set of switch positions will produce a unique number. The same number will not appear with two different sets of combinations, so that number will always correspond to 4 and 8 being switched on. So I can now send that number via our memory, which is in there, state 12, across to the other machine, and then I can just decode that to switch on the corresponding lights. Now it's all coming from one value. I have used the memory there. One side of the circuit is connected to this one. The other side of the circuit is connected to the other one. So I can't cheat here. I can't read any of these switches from this machine over here. But there we go. So that's what we've got there. That is our coding. So to decode it, that's a tricky part because it's in a number at the moment. That's fine, but that doesn't tell me which light's meant to be on. So we shall set this up with our corresponding lights. Cool. Right, now we have once again our display, our lights and our memory all aliased in to the corresponding pins. Now we want to take the value from the memory. Once again I shall alias data to R10. And that will be what we read from the memory. So first thing we've got to do is load it in from the memory. So load into data memory setting. Right. Now we have that in. So now we have to actually decode it. So we're going to have to isolate one of the values from that and then find out what it's like. Right, so the first one is pretty easy. So the one switch is pretty easy to get, because if it's odd, the on switch is on. If it's even, the on switch is off, or the one switch. So all we have to do is use a command, which is mod. So what mod does is it will divide by a value and keep the remainder. So we shall say R0 equals data mod 2. So we divide by 2 and keep the remainder. So once again, if it's even, the remainder will be 0. If it's odd, the remainder will be 1. So we shall then save to the display. Yeah, that's not right. Display setting R0 and jump to the strat. Jump to the start perhaps. Okay. Confirm. Export. So there we go. Switch on the 1. It knows there's a 1 there. It's off. If I change the other ones, it makes no difference because it's just isolated the next value in there. Easy. So we can write that one to the first switch. Okay. Easy. So we save to light 1 on R0. Boom. That's easy. That's the first one there. Export. There we go. First light works. Now the second one. The second one's an even. Well, all the rest of them are even numbers now. So that poses a little bit of a problem for us, because we can't use that same number. And if I divide everything by 4, there will be a remainder if the one switches on. So we're going to have to try and isolate the next signal in all of that one. So what we do with that one there is we're interested in the number 2 value. So from that one we have memory. So the data still has what we want in it. So we shall, this time we divide by the indexer. So the first one, well, you divide by 1 and then mod 2. Dividing by 1 doesn't do anything, so that's pretty pointless. But the second one, we shall say divide R0 equals data divided by 2. And we shall display that on the display. Export. Right, so the 2 switch is there. So it's value 10. It's there. Right, so if that is off, we have an even number. If it's on, we have an odd number. So once again, I can just mod 2. But we do have an issue there that if that one's on, that one's off, I still have a remainder. If I divide that by 2, I shall have 0.25. Or if I mod by 2, the remainder will be 0.5, which will still be a true value. So we first have to truncate any decimal places off that one. So we've divided by the indexer, which is 2, and truncate R0 equal a truncated R0. So export that one, and it has ignored the decimal point. So whatever that one is, it's ignored the decimal point, and all we have now is the ones above it. So we've divided by the indexer, truncated to get rid of all the rest of them, and now all we have to do is perform the same odd-even test, and we can identify that one. So once again, copy you into there, and we're done. Not data, it'll be an R0 because it's a progressive one there. Confirm, export. Now we have a 0, it's off, and there we go. We have the next one isolated. No matter what we do with the other ones, we still have a 1. Right, so we just repeat that for the next ones. So once again, we shall just sort of say, copy you. So light 2 will be switched on by that. Now once again, we just repeat it for the other 2 switches. Right, so there we go. We just copied that 3 times. Now, to get the second position, once again, we divide it by our indexer, which is now 4 for the third one, and 8 for the last one. And other than that, each line's the same. We just truncate it, mod by 2, and switch on the lights, which will be the other lights perhaps. 3 and 4. Export. And there we go. So light 1, switch on and off. 3 on and off. 4 off. You can now read these ones there through the 1 value. It is now able to decode that number into the on-off switches for all of them. So once again, you can add on more and more. So if you have 20 or 30 process variables that you need to pass from one to the other, of course you're not going to be controlling 20 or 30 items there, but you may have something in your program there that has a heap of variables that need to be transferred. You can just copy them across, encode them into a single number and send them across that way. I mean, that works fine there if you have only on-off switches, but what if you have something more than that? What if you have, say, a series of numbers there that can have more than just an on-off value? So some dials. We can do the same, well, not the same thing, but we do a very similar thing. So if we switch those ones out to a set of dials, I'll also have to switch my lights out because they can't display what dials are doing. So I'll put some displays in there and we can decode them. Now if each of these dials have, say, 10 possible values, it is just a matter of changing these ones here. So the index of the first one will still be 1. The second one can have 10 possible values, so the next one will have to start at 10. The next one, of course, will be 100 and 1000. Right, so there once again, we've got 10 numbers there, so we'll have 10 to the power of 0, which is 1, 10 to the power of 1, which is 10, 10 to the power of 2, which is 100, and 10 to the power of 3, which is 1000. And we shall have to put in some displays here to decode it. Right, so here we go, we have our 4 dials hooked up, we have our 4 displays hooked up. Right, now on our code, we shall do the same, well, something very similar. So they're not levers, they're dials now, but yeah, get over it. Right, so the first one, we're multiplying by 1, but doesn't do anything, so why bother? So our second index there, we should multiply by 10. Our third index is 100, and our fourth index is 1000. Confirm, export you. I had better switch my dials up so as they work. Right, so each of the dials now have a maximum setting of 9. So 0, we can say, boop, there we go, it'll give us a 1. 10 1 will obviously just give us a 10 value, and the 100 value, and the 1000 value. So once again, we are no longer binary encoding, we're now decimal encoding, which is just a lot easier for everyone to understand. So once again, it's the same sort of thing. We have just multiplied by the index and added them all together. So same code, all I did was just change the indexes. Now on the decoding side of things, it'll be a similar sort of thing again. So I have all of our displays. The displays now, they're not lights. Now, it's our first one. We divide by the indexer, which is 1, which is pretty pointless, and we truncate it, which once again is pretty pointless because we divided by 1. And then we mod by 2, and that will get us, actually we don't want to mod by 2 anymore, we want to mod by 10, because it is a decimal number, so we want to divide by 10 and keep the remainder. So that'll give us a value anywhere between 0 and 9, which is what they're capable of the first dialer setting. Okay, so our second one, our indexer is 10. We are once again modding by 10, so we want a value between 0 and 9. And our next indexer is 100. And our step is 10 and 1000. Once again, we mod 10. Confirm that, export it, and there we go. We have our value decoded, separated out onto each of the ones there. So we can now use each of those separate values from all the process variables. We've now split them back up and we can use them in the other half of the program. That works values from 1 to 9. Once again, you can easily set a double-digit value. If you set it to 1, 100, 10,000 and a million, you can send through 4 double-digit values. It's just a matter of scaling up. The more settings you have, the more you have. But that's it there. So that's what we've got. That is your numeric encoding. You can sort of send as many values as you want and just retrieve them all at the other end via a single value. Of course, this one can then write back using exactly the same process to send some values back again. So that should allow you to expand your programs beyond one chip and communicate all the environmental variables you need to continue the program on the other chip. Now, I have used some very basic parts of this before. As part of my Harvey script, I've got a greenhouse manager which actually writes a value to the Harvey housings just to tell it whether or not the room is safe for planting. I have another chip which manages the greenhouse and a chip that manages the Harveys, and I just want the greenhouse to tell the Harveys when the room is safe, because Harvey's pretty clueless there. So that's only sending one value. This one you could send a whole heap of values for whatever reason. How you use it, I'll leave that up to you. I have been asked about it, and that's numeric encoding. That is a very powerful way to communicate between different programs. So there you have it. I hope that made sense. It's pretty heavy going if you're not used to numeric. The binary encoding is probably a bit alien for most people, but the decimal encoding is probably an easy one. If you're new to all this sort of stuff, I'd say go with decimal encoding for your first attempt. It's just a lot easier to picture. But there we go. So use that how you will. But until next time, happy building. See ya.